What's up, ladies and
We'll
gentlemen?
be on the outtakes.
What's up, ladies and gentlemen? Welcome back to Engineering Tomorrow, your number one podcast for commercial construction, HVAC, and engineering. Today, we are on the road in Kansas City taking an in-depth look at cooling towers and fluid coolers. What are they? When are they used? And some great applications you may not have thought of. And as a bonus, our guests will be sharing their secret championship rib recipes. Rib recipes. So sit back, relax, and prepare for your mind to be blown.
Broadcasting around the world. This is Engineering Tomorrow, the podcast committed to bringing you the best in commercial construction, design, and engineering from the brightest minds in the industry. This is the stuff they don't teach you in school. So sit back, relax, and open your mind. You're about to get the insider knowledge to improve your next construction project or advance your career. This is Engineering Tomorrow.
Hey, Engineering Tomorrow fans. We are here, obviously not in our normal studio, in a very special location in Kansas City. We have two incredibly special guests, and we are glad that you are here today. First, we have Troy Gladstone, president of Midwest Machinery. Today, we have Troy Gladstone, president of Midwest Machinery. Cue the applause. And also Spencer Kaufman, one of the smartest and top sales engineers in Kansas City for commercial HVAC. How are you guys doing today?
Wonderful.
Fantastic.
Do we get to do call out retakes whenever we want? Because
nope.
You had 4 of them.
Only the guy editing gets to do the retakes.
It's a traveling studio. You gotta give him a break.
Since we're picking on you, can we talk about your shirt
Oh,
first?
absolutely.
So do you know if the shirt is on camera?
The shirt is on camera.
Okay, so this is the loudest shirt I've ever seen in the HVAC industry. It looks like, I think it's geraniums, but I'm not sure. I just want to call attention to that.
It was when I walked into the Banana Republic outlet, it was on the mannequin. And I said, give me that outfit. So fast forward, here we are today.
Spencer, what would happen if you showed up to your top engineering firm with that shirt on?
They would say, we're making Marley bases of this.
Oh, all right. Never mind. That was not what I was expecting. So
nothing speaks confidence.
So can we get that with the Midwest Machinery logo on it, Brian?
Absolutely. I think a lot of engineers love the new green movement. So this is
all right.
It speaks confidence. Nothing speaks confidence more than a man wearing a flower shirt.
Absolutely.
Well, this is true. Yeah.
So, guys, what are we here today talking
about? Oh, that's right. Yeah. So one of the most recent podcasts we did was the epic battle of Counterflow cooling towers versus Crossflow cooling towers. And as we were at lunch today, Spencer and I were talking, and he said, I get a lot of questions about fluid coolers, and when should I use fluid coolers versus cooling towers? Mm-hmm. So it seemed like we're here, seemed like a good topic to bring up,
and Brian just happened to have 3 microphones.
Just in my trunk, ready to go.
Right.
At all times.
Right.
I would like to point out
master marketer
to anyone listening.
Your gimbal just flipped out. I don't know if it's still recording.
Cool. It did a backflip.
Do you know was it still recording?
Yeah.
Okay.
I would like to point out to anyone that is listening in their car or on podcast, we are now on YouTube in video format. So to see our lovely faces and the shirt that I have been made fun of for wearing, please search for Engineering Tomorrow on YouTube. With that said, back to cooling towers and fluid coolers.
So, Troy, who won the battle? Crossflow versus Counterflow?
Well, the final conclusion was that Crossflow is the hands-down champion.
Okay.
Specifically, an induced draft Crossflow cooling tower.
Okay.
And really, it was the best combination of space, ease of maintenance. With ease of maintenance comes the actual probability that maintenance will be done, because if it's not easy to maintain, it won't be done. And then energy, and finally operation in cold weather, which,
Yeah.
almost all of our offices operate in cold weather. So it just doesn't freeze up as much as a counterflow tower. But, counterflow certainly had its spots, specifically in very tight footprints. Sometimes the counterflow is the best fit.
Right, under specific tonnage, right?
Yep.
So Crossflow versus Counterflow applies in fluid coolers as well. So maybe we can tell the audience the difference between Crossflow and Counterflow.
Can I ask a question? What's a fluid cooler?
Oh.
I think we have an audience that may have never used a fluid cooler before.
We got to define a lot.
So
of
maybe
stuff.
we even go back a step back and say, what's a cooling tower?
Okay.
Go for it.
You go cooling tower, I'll go fluid cooler.
All right, fair enough. So we're predominantly talking about products that use water and evaporation as the means of cooling. And, there is no more efficient means to cool a BTU of heat than evaporative cooling. Mother Nature has the best, most efficient system. And so many applications use evaporative cooling. So the simplest form is a cooling tower. And when we talk about a cooling tower, we'll often describe it as an open circuit cooling tower, where we have process or a chiller, for example, that needs to be cooled. You've got a condenser and a chiller or a heat pump, or you've got an air compressor or quench tanks in an industrial facility. Something needs to be cooled, and we take that processed water, we run it over a cooling tower. We'll say over a cooling tower because we use gravity in cooling towers, and we drop that water through a fill media. We call it fill, pretty creative, through a fill media, and we generally pull air across that, and we evaporate. And through the power of evaporation, we'll affect usually a 10 to 15 degree temperature drop, all based on the dry bulb temperature and humidity, or we call it the wet bulb temperature. But we affect a temperature drop in that cooling tower, and then that cooler water is then returned to the process or the chiller or the heat pumps or whatever have it. And we call it a cooling tower, and we call it open because if you think about what a cooling tower does, is it's pulling in massive amounts of air, and that air comes in contact with the water, and we call it an amazing air filter. Because anything that's in that air has the potential to be transferred to the circulating water system. So in a cooling tower, and I'm rambling, but in a cooling tower, the great value is we do a tremendous amount of cooling for very reasonable first costs, but it comes with a downside of having to manage the water treatment specifically with the contaminants that come into that water and can come in contact with your process or your chiller or whatever have you. So that's a 10-minute or less definition of a cooling tower.
Super efficient cooling.
Right.
The most efficient version, but you got to take care of the water. So
very much so.
Like a pool.
Yeah. I'm a Southwest Kansas guy. And when I first started my tenure with cooling towers, the best way is explained
Which was
to me,
at Marley. You
which
worked
was at
for
Marley. Yep, directly for them in the applications department. Shout out to that team. Hope some of them are listening.
Rest in peace.
The best way it was explained to me is, okay, it's 105 degrees in Dodge City, Kansas, but there's no trees. It's the desert, right? So you're out at the farmhouse and you go swimming in the pool, and it's 105 degrees out. And magically, when you get out, mind you, when there's no trees and it's a flat desert, it's very windy. When you get out and you're covered in pool water into the wind, even though it's 105 degrees out, dry bulb, you're magically cold. And that is the power of evaporation. So that's basically a cooling tower on top of your body. So
your definition was better than mine.
And I did it in probably about a tenth of the time.
Oh, well.
Yeah, no, that's good. I
Right.
strategically asked you to define cooling tower because now fluid cooler is so much easier.
You took advantage of my long-windedness.
Yeah. So all a fluid cooler does is take that water that you're trying to cool, that processed water, and take it from an open loop system like you would have on a cooling tower and put it inside of a coil so that it's a now a closed loop system, so you're not worried about the outside and contaminants. There's a few different ways to do fluid coolers, right? You can do a dry cooler to where you have the process water you're trying to cool going through the coil, but you don't have a separate loop spraying water over the coil.
So it would be non-evaporative.
It'd be non-evaporative. That's the least efficient way to do
Dry
it.
cooler.
It's called a dry cooler. Yep. So you're just using a fan to pull or push air across.
Basically a radiator.
It's a radiator for your car, used in HVAC, exactly, or industrial, whatever. So that's one way. And then you can add water to it. There's some other more advanced stuff like adiabatic and such, but we probably just hop over to the evaporative side, where now you have a separate open loop going over your fluid cooler coil to cool that coil down and use the power of evaporation to cool that process water down. So the water connected to your condensers or your process is protected from the elements, but you have a smaller, much more manageable open loop system taking the heat off of the coil.
And, a good point there is that doesn't necessarily have to be water either inside that coil on the
Correct.
process side. It could be a water glycol mixture so that we don't have to worry about freezing. It could be a process-related liquid. Could even be refrigerant, where we would have what we call an evaporative condenser.
Mm-hmm. Yep.
That's really the only point I had. So you're looking
Great
at
points.
me like I have to keep talking.
So you take that back. What was the original question? I think it was difference between crossflow and counterflow.
Right. So yeah, it's essentially we've taken a cooling tower. I always like to use the analogy of we've taken a cooling tower and added a heat exchanger in there. And so when you think about it in those terms, is we've now separated the atmosphere from the process load with a heat exchanger, and that creates a little bit of inefficiency. So there, if we're talking about cooling tower versus fluid cooler, I say we already have our first advantage for the cooling tower, which is we're not adding a layer of heat transfer.
Correct.
You tracking with me?
Yep.
Okay. So what does that mean? With cooling tower, direct contact, direct evaporation, sensible latent cooling. With a fluid cooler, we've now added this coil, and we'll probably talk about the materials of construction for that coil in a little bit, which is really important.
Are you using heat exchanger and coil interchangeably?
Exactly.
Yep.
Yeah. So so it's an air to water heat exchanger. Sometimes with our hybrid fluid coolers, it's a air to air essentially heat exchanger. We're not using water. Did I just misspeak? Edit that out.
No, because that could happen too, right?
Yeah.
When you're running dry.
Yes.
The reason I think you almost misspoke is because
It's not
there's
air to air.
so many different ways you can do it, and hopefully
Right.
we can tackle a lot of those on this podcast.
Yep.
But I do want to go back to crossflow versus counterflow, because I think a lot of people hear crossflow. I know I need crossflow, but what's the difference between counterflow and crossflow? So all that is the interaction in the air and the water. So if you think about a cooling tower, you have water falling down, right, across the fill. That's really the heat transfer media. And then on a crossflow, you have the for those watching, it's easy. I'm trying
Hopefully
to think
we'll
about
put a visual aid in here.
I'm doing spirit fingers. So you have the water trickling down, and then on a crossflow, the air is coming across the water, and that's called a crossflow.
So the air is coming in from the side.
Yes, from the side. If you have a counterflow, the water's still falling down, right? Gravity, earth, that kind of stuff. But the air comes in, up under, and turns up, and comes from the bottom, and it goes counter to the falling water. So that's the main difference, but that really doesn't define why one's better than the other. It's just the way the design is, the way you design the cooling tower and or fluid cooler in such a manner so you get the counter or cross flow air to water interaction is what gives you the other design aspects of that cooling tower or fluid cooler. We're going to get into cross flow fluid coolers and counterflow fluid coolers. That's why I really thought we should take a minute to define.
Yeah. So it might be good if you're interested in learning more about the difference between counterflow and crossflow in context of what we're talking about today, to go back and watch that podcast, because most of the same arguments for or against one or the other apply here as well.
Yeah, absolutely.
All right, what's next?
Host?
I'm asking you what's next because you're staring at the whiteboard.
It's that simple, huh?
Yeah.
It's that obvious, I mean. Okay, so we talked about the differences between a cooling tower and a fluid cooler. We have you think we've defined an open circuit well enough versus closed circuit?
I think so.
Okay, that's the
With
main
or without a
difference.
heat exchanger.
Yeah. So now we need to talk about when we use a fluid cooler versus when we use a cooling tower.
Sure.
That's the age-old question, isn't it?
Says the man in the flowered shirt.
Right. I'll throw out a reason. In process-related situations, so when we talk about process, we're talking about not HVAC, not air conditioning. So in process-related conditions, we'll often be at a facility that, in addition to being an industrial facility that by nature sometimes are dirty, sometimes they've got contaminants in the area. We do a lot of corn sweetener processing facilities, and those plants are literally installed in the middle of a cornfield, and they have an application, maybe it's an air compressor load that needs cooling, and if we put a cooling tower in there, just the amount of organic compounds that through their process and through just being in the middle of a cornfield it sees leads to just an unacceptable level of water treatment that's needed. So oftentimes in industrial processes, we'll put a fluid cooler in, which allows us to separate their process load or the small heat exchanger jackets and air compressors from all of that ambient dirt and processed dirt. And then we're able to really treat the spray side of the fluid cooler with the more aggressive chemicals or physical filtration. So that's my first reason to use a fluid cooler, and I took the easiest one.
Yeah, I think that's industrial, so then you hop over to HVAC. Now you're talking about, okay, where would you put a fluid cooler?
Where do you see it most?
And in 99% of my fluid cooler applications, it's going to be in a water source heat pump application. So you see this a lot for school districts. Some retail stores are even switching that way. That's not as common, but it's
some government buildings. Sometimes you'll see
buildings.
bank buildings. Typically you'll see water source or geothermal or hybrid, which we'll probably get into.
Yeah, we definitely should.
In end users who are owners and operators with a long-term perspective, because it can be a little bit more of an upfront cost compared to a cheap package rooftop system, but the payback is there in terms of the energy savings.
100%. It's all back to you get what you pay for.
Right.
So on the heat pump side, they're doing that because they don't want the contaminants with it flowing through the loop within the building.
Maybe step back and quickly give a 30,000 foot elevation of what a water source heat pump system looks like, and maybe even a geothermal.
Absolutely. I'll do my best. You fill in where I miss. And I think we even reference back, we have a heat pump podcast too. Didn't you do? So maybe you can link that up and provide that as context. But in general, you'll use a heat pump system, and you'll have individual terminal units in a certain space,
like in a classroom or a hotel room or a condo.
Yep, you could put them as small as a hotel room or as big as the main
cafeteria
or cafeteria. Yeah. So, but what you do is you have the compressor and the refrigerant circuit at that unit. So whether it's in heating or cooling, you have the versatility to pick which mode you need to be in at that space, and you're not subject to be in the mode that the rest of the building is in. So that's the main, in my opinion, benefit of it.
Yeah. So the key feature of a heat pump is I always love to talk about, we are pumping heat throughout a building.
Yeah.
And each of those terminal units has a reversing valve in it that allows the heat exchanger in that heat pump to either act as the evaporator or the condenser. And so we're moving heat from the classroom, or we're pumping heat into the classroom. And then that heat gets dumped into a circulating loop that travels throughout the building. And then that circulating loop needs to maintain a relatively consistent temperature.
Yep.
And we either, depending on the time of the year, we either have to supplementally heat that loop, or more often we have to cool that loop.
Yeah. Or if you're really lucky, it balances each other out.
It balances each other out, but it never balances itself out over the long run. So, there are times, and now we're really getting into the weeds of a water source heat pump system or geothermal heat pump system, where you can have a large portion of the building providing heat to a portion of the building that needs heat, and vice versa. And that's the perfect balance, and that's why heat pump systems are so efficient, because we move heat from, let's say, in the afternoon, the west side of a building. We move the heat out of there to maybe some areas in the building that are cool, that need some heat.
Yeah.
But that doesn't happen very often. But what I was really talking about, why would we need, in a water source heat pump system, why would we need to add a cooling tower or a boiler? It's because in the wintertime...
Fluid cooler, preferably.
Yeah, thank you. Well, that's why we haven't discussed why we would put a tower versus a fluid cooler in. So maybe it leads me right to that. So why would we put a fluid cooler in a water source heat pump system?
Yeah, it goes right back to Troy and I defining closed loop versus open loop, and a cooling tower versus a fluid cooler. When you have, say, 100 heat pumps in a building, each little heat pump has its own refrigeration cycle, its own compressor. So the last thing you want to do is subject the outside environment and ambient conditions to all of those little compressors.
Right, yeah.
And then you start replacing compressors and heat pump components.
Yeah, because you clog that coaxial heat exchanger where we've got water on one side, refrigerant on the other side. Yeah. And as soon as we lose water flow because of a clog, which could have been, it could be anything. Usually it's just an abundance of dirt and then an abundance of minerals that builds up to create scale.
Yeah.
And if those aren't managed, then
you've got a problem.
You foul those heat exchanger surfaces. So it's not always even that you clog it so it doesn't work. It's just that we layer up those heat exchanger surfaces with calcium or scale or dirt or bioslime, and then we lose efficiency throughout the whole building. So putting in a fluid cooler separates that so that the water going through those heat exchangers or the water glycol mixture is pure and clean, and you never have to worry about it.
Yeah. And back to our definition, water source heat pump, that means a heat pump connected to a water loop.
Yep.
So you're rejecting the heat that, if your building is in net cooling mode, you're taking that net heat that you need to reject. It's dumping it from the heat pumps to the water loop. That water loop is connected to your fluid cooler coil, and then that fluid cooler rejects that heat to the atmosphere.
Exactly.
Yep.
Super efficient.
So
it's all, there's a lot of debates on the most efficient system, whether it's...
Is there?
People talk.
A lot of folks, and there's a lot of evidence out there to say on a given project, the water source, or specifically the geothermal heat pump system, is still the gold standard for efficiency.
Sure. That probably is, right, the gold standard, but we have capital constraints usually. So, Troy, we didn't even plan this.
Uh-oh.
How do you save capital costs when you want the efficiency of a geothermal system, but you can't afford it?
Oh, great question. One of my favorite systems is a hybrid geothermal system. So to go back, we talked about what a water source heat pump system looks like. If we talk about, when people think of heat pumps, they traditionally think of geothermal heat pumps, where instead of having the fluid cooler or a boiler to add heat in the wintertime, we take that loop down sometimes hundreds or thousands of feet into the earth, where we have this wonderful battery of mass called the Earth's core that keeps a very consistent temperature. So we therefore use the earth as our heat sink or our heat source. And it's wonderfully efficient,
Yeah.
but it's also wonderfully expensive. And so you'll see a lot of sometimes utility rebates for geothermal systems, federal rebates. There's oftentimes a lot of incentives to go with geothermal, but even with those, sometimes the first cost is too much for somebody
Yep.
to swallow. So what we love working on is these hybrid systems where you take a school in
Dubuque,
rural
Iowa?
Missouri.
Dubuque, Iowa.
Well, in Missouri,
You're in Kansas City.
Sorry.
so
Right.
whether it be
So
Kansas
Dubuque's
City
funny.
or St. Louis, where winter design is somewhere around 0 degrees Fahrenheit, and summer design is dang near 100 degrees Fahrenheit with very high wet bulb. In those applications, the engineer is going to calculate your heat gain and heat loss of the building, and your winter design and your summer design. And if you're doing a 100% geothermal system, you have to put in the well system to accommodate which of those is greater. And in our markets, all the markets that we serve,
Cooling.
it's always cooling. So cooling drives the size of the well. Well, so if we want to have geothermal and get incentives, but also want to save some significant upfront costs, what we can do is instead of sizing that well for the cooling load, let's size it for the heating load, which then allows us to get rid of our supplemental heat system. And then whatever that well that can handle the heating load's ability is to cool, we pick up the rest of that with a fluid cooler.
Yeah.
And those are awesome systems because it gives you the assurance of being able to, handle load on the hottest part of the day, but the grand bulk of the time that geothermal well is able to handle 100% of the load. And you save a ton of money because it's a much smaller well and you've gotten rid of a boiler system.
Which is incredibly important because a lot of these systems are serving rural markets, and these rural communities don't have the money to dump into a full geothermal system.
But it's so important for them to have an efficient system because the power grid sometimes can't supply the demand.
Yeah.
So you're kind of stuck in this mix of an energy company offering some pretty awesome rebates so that they don't have to increase their capacity, but you can't afford to put in the system that they're trying to rebate.
I think that's the Willy Wonka golden ticket.
It is, yeah.
You can send thank you notes to Midwest Machinery, Lenexa, Kansas.
Yeah, so it's an awesome system and just a fantastic application for a fluid cooler.
Yeah, so those are really the main two. I mean, basically the theme is isolating the components in your system from the outside ambient. You can also use it in water-cooled VRF. Right?
Yeah, that's another. Well, this is where that whole debate of which system's more efficient. Boy, it's tough to argue with the water-cooled VRF system.
That's an efficient system.
Super efficient. Pretty expensive. VRF is not the least expensive. We do sell it, but it's not the least expensive. But it's a very efficient system. Why would you, Spencer, say some people choose a VRF system over a water source heat pump system?
Gosh, I don't know if I'm the person that can fully answer that, but if I was to pick VRF over water source, are you saying water-cooled VRF or air-cooled VRF?
Just traditional air-cooled VRF.
Well, I think you can pack more punch of energy in refrigerant than you can water. So that's one thing I think about as an engineer. You've kind of put me on the spot here. The other thing is you maybe get more control.
Do you need to call in a friend?
Yeah. Is there phone a friend?
Yeah.
Yep.
Correction, disclaimer. We do not sell VRF in the Kansas City market.
Well, we do in other markets as well.
In other markets, yeah.
Midwest Machinery has a big footprint. Sorry.
Yes. So can you bail me out?
Yeah, I'll bail you out. So I think one of the largest reasons that people have, in many scenarios, moved from water source heat pump to air-cooled VRF is fear of water treatment. And I'd have a lot of arguments against that because I'm, at my core, I'm still a water-cooled person. And I just think that it's tough to overcome the benefit that Mother Nature gives us. But I think a big issue is they have this fear of water treatment. So salespeople have been able to, key on that fear and say, well, let's get rid of that water problem and give you a air-cooled VRF system that has, X, Y, and Z benefits. So we're not here to debate that right now.
That's a different podcast.
But it is a good debate.
I won't be the guest on that podcast.
All right, sounds good.
Well, I to salvage myself, I asked that I had that thought, but then I said air-cooled or water-cooled VRF, and he said either. So I was thinking,
I thought
maybe that's not the
air-cooled.
answer teachers looking for.
But it's a good point, though, that fear of water-cooled is actually going away because people are still seeking more energy savings. So that's why we're seeing a very big increase towards water-cooled VRF, which we do endorse.
Yes, and there's a lot of benefits of water-cooled versus air-cooled VRF, but that's a different podcast.
It is.
So we covered everything, basically most of the applications, at least from a high level.
Going back to geothermal, the hybrid system seems like it makes sense. Can you talk about on rare occasions when a existing loop suffers from hot loop?
Oh, yeah. That's a great one. You want it?
Yeah, I'll take a little bit and you can elaborate. So Troy canned the term of geothermal remediation, which I think is fantastic.
I don't think I canned it. I heard it somewhere.
Okay, well, you stole it from somewhere and I'm stealing it from you. We'll recycle it. So basically you're taking a fully geothermal system that is in some trouble, and you're adding a supplemental fluid cooler to it to get that well field back into a more stable condition.
And it gets in trouble. Sometimes the wells weren't properly designed, meaning the well itself isn't big enough to handle the load. And over time, you have to think about that geothermal mass as a battery that charges and discharges. And sometimes we charge that battery with so much heat over the years that it just cannot keep up. And that's when we'll sometimes put in a supplemental fluid cooler. And we like water-cooled in that instance. We have very simple water treatment and water maintenance programs so that it's almost turnkey. But that rescues a lot of school districts who are having cooling problems. And, a lot of people are looking to get rid of their geothermal heat pump systems and replace it with either really junky air-cooled PTACs or univentilators that are energy hogs when all they really need is a helper for their geothermal loop.
Have you ever heard of do you know if loops can ever recover, or is it permanently considered a hot loop?
Oh, no, that's exactly what we're doing. That's why we'd put the fluid cooler in there, to recover that loop. So it does and people get really fancy with the controls, and there's good reason to. So sometimes it's, they'll run the fluid cooler at night to think of it as a battery to discharge that battery. Sometimes they run it at peak or off-peak times because energy might be cheaper at 2 o'clock in the morning than it is at 5 p.m. So there's all kinds of different strategies you can use to recover that loop.
Yeah, and even in hot climates, not only is energy cheaper at 2 a.m., but the wet bulb temperature is a lot lower, so you get a lot more efficient cooling, so you can reject way more heat out of that loop at night than you could during the heat of the day. So if you're clever and you size it right, you can save yourself a lot of money.
Yeah, so and this is where you get really nerdy in the controls. It's not so much that you're running that fluid cooler in the hottest part of the day when there's the most demand. It's, if we're really smart, we're trying to run that fluid cooler at the smartest time of the day to discharge that earth battery so that it can then pick up more heat in the peak of the day.
Yep.
Those are really geeky conversations that I think are awesome, actually.
Yeah, that's what makes the job fun.
Sometimes.
Are you putting the fluid cooler before or after the loop?
It's the same.
It's the same.
Doesn't matter.
Yeah.
It's in the loop, and it's a loop.
Yeah.
So then you're running
depending on what
bypass then during the day off the fluid cooler?
No,
or-
it's just literally in the loop. I mean, yeah, so
because you said you were
could.
going to run it
Yeah.
at night, so I wasn't sure if then you're bypassing it during the day or.
Well, you could run through the coil and just not turn the fan on, or you could
Gotcha.
bypass the coil
right.
during the day. However you wanna do it.
Probably the greatest energy saver would be that you would have almost like a primary pump on your fluid cooler, so you're injecting into that loop, into the circulating loop. That way, when we're not using the fluid cooler, we're not pushing the full loop water through a smaller, higher pressure heat exchanger. So we're saving pressure drop when we're not
Yeah.
utilizing the fluid cooler.
Which means you can slow the pump down.
Yeah.
Yep. Save
Well,
energy on that.
Yeah, all
That's
right.
what
There's a whole nother variable primary conversation that we need to
Sure.
have a podcast on.
Yeah. Are you writing all, Mr. Host? Are you writing all these podcasts?
I'm recording it.
Okay. There's actually two. While we're in applications, there's literally two specific jobs I'm working on right now. Well, there's more than that in terms of heat pumps. and
Like,
fluid
really?
coolers, but
You need to work on more than two at a time.
there's two that I'm working on today and yesterday that I really want to bring up in terms of application. And the first is the geothermal remediation. That's huge. There's a government building, I won't say where. I'm not sure if they'll come and get me and put me in a car or not. Where their well field is putting temps back to their heat pumps at like 110 degrees in the middle of summer. That's hot. So hot. Not really a great.
It's not ideal. Dick, you can
Yeah.
actually cool with that, but
Can.
your efficiency of the units has dropped.
Yeah. And would you
Huge.
say your lifespan of your compressors
Oh yeah,
goes down?
yeah. It's like running your car at 4,000 RPM all
Yeah.
the time.
You could do it, but you're gonna have some problems later down the road.
Yep.
And it's not as efficient. So they came to us with that problem. How can we help? Someone else is trying to tell us we should put chillers in, switch out the system, change it up. And I'm saying, how about we start with a remediation first, see where that gets you. And they're going to do exactly what we talked about. They're going to have a main primary loop serving the well, and then we'll just have a secondary loop pulling off that and
Yep.
injecting back into that. So that's the first one. Another one is new heat pump systems, but they're being sized for dry coolers, dry fluid coolers. So remember, audience, dry fluid cooler means you don't have that second loop to use the power of evaporation.
No spray pump, no
No spray
basin.
pump, yeah.
It's a radiator.
It's a radiator. So now they're not even doing it on accident. They're purposely designing for 110 degree loop temps. And the reason those loop temps have to be higher is because on a dry fluid cooler, you're cooling to the dry bulb and not the wet bulb. Dry bulb's always going to be higher than the wet bulb in a cooling scenario. So I'm saying, okay, if you want to maximize the efficiency of your heat pump system, let's check out an evaporative fluid cooler. And now you can get your loop temps down to 95, 85 or something a little more manageable. And your heat pumps are going to operate so much more efficiently and last longer. So those are literally two jobs I was working off before this podcast. So I was like, I really got to talk about those. Perfect application example.
And maybe a good segue into some types of fluid coolers.
Yes.
In that particular situation, might be a type to use a hybrid fluid cooler.
Yeah, that's exactly what we're doing. Yeah.
Okay. So explain what a hybrid fluid cooler is.
Mm-hmm. So hybrid fluid cooler is, just to re-summarize, you have a dry cooler with no circulating loop, and then you have a evaporative fluid cooler, which has your coil, but then a circulating loop spraying over that coil, rejecting the heat using the power of evaporation. So that's your evaporative fluid cooler. But to even go deeper into the weeds, on your evaporative fluid cooler, you can have a hybrid fluid cooler. So basically what you're doing is you're introducing some fill media like you would see in a cooling tower into the open loop of the fluid cooler. So you have the closed loops going through the coil back to your load, and then you have the open loop, right, that's spraying over the coil. So what you do is you take that hot water that's just gone over the coil and taken all that heat from the process, you pump it back to the top of the fluid cooler, and then it goes into a gravity distribution system and then sprays over the fill, just like you would in a cooling tower. So it's like you're putting a miniature cooling tower inside your fluid cooler.
So if we were to put an image up on the screen, what model Marley are we talking about?
There's 2 fantastic models. So I'm actually working on more than 2 heat pump jobs. And in one of those applications, a smaller tonnage, we would use like the LW.
Okay.
It's a Counterflow hybrid fluid cooler. It has direct drive fans, plug and play controls, all that jazz. We can dive more into that
motors.
Later. Yeah, ECM, where you can get them with just the standard
Well,
direct drive. Yeah.
Traditionally ECM motors, but now in our
supply chain
shortage.
Yeah. So that's the LW. On the other jobs we're working, it's going to be what we call the MHF, and that's a Crossflow fluid cooler. So that goes back to why we want to define Counterflow versus Crossflow. So there's inherent advantages and disadvantages to each. But the MHF is going to be for your larger tonnage type stuff. And I like to use what we call the MHF element, which I think segues into coil material choice.
All right, perfect.
I like MHF element because it's a copper coil. So maybe you can elaborate on the 3 choices and why and
Sure.
when.
Yeah, absolutely. If you go back to thinking about these fluid coolers, we're predominantly talking about evaporative fluid coolers. And when we take water that comes from a spigot, we call it city water. Mm-hmm. Is that water perfectly pure, Spencer? No, it has hardness in it, right?
Yeah.
Because, the water that we're drinking has hardness in it, calcium,
elements,
magnesium, all kinds of different elements. But the problem is, whether it's a cooling tower or an evaporative fluid cooler, is when we evaporate water either on filled material in a cooling tower or a coil surface in a fluid cooler, that mineral content, those dissolved solids, any of that hardness stays behind. And so when that hardness stays behind, especially in fluid coolers, it often adheres to that coil, the hottest place in the vessel. So it's really important to think about materials of construction, and you have to balance first costs versus maintenance costs and efficiency. Yeah. So if we start on the low end of the spectrum and we're talking about first cost, we have a steel coil that is galvanized.
Yep.
That is by far the least expensive coil material you can get. And the very best day of its life is day one. And from that point going forward, you will lose efficiency.
Diminishing returns.
We're 100% sure that you will lose efficiency after day one. And why? Because we're just constantly evaporating on that coil, and the zinc is ultimately a sacrificial coating. So it has a limited life expectancy. Once we lose that zinc coating, then we replace it with iron oxide.
Is it true?
Rust.
If you don't use it, you lose it.
Oh gosh, yeah. Yeah, but so with a galvanized coil, it's the least expensive coil to put into a cooling tower. It has pretty good heat transfer.
Yeah.
But so if you don't perfectly treat that spray water that's in a fluid cooler, you stand a high probability of scaling up that coil. And so when that happens, let's assume we have a less than stellar water treatment program in place. When that happens, what does that less than stellar water treatment company do to take care of a fluid cooler or cooling tower that is scaled up?
Well, first I have to say, if you have a good water treater, pay them higher than what they deserve and don't let them leave.
Oh yeah, for sure. Yes.
The first thing they're going to do is blame the manufacturer.
Always. That is 100% the case. Bad metal.
Yeah. The second thing they're going to do is dump it with acid.
Yeah, because acid is cheap. So they're going to start loading up the tower with acid, and that does an amazing job of combating the scale. So it cleans up the coils, cleans up the water, and it strips the zinc off. And so as soon as we start,
they didn't tell me that.
Right. Yeah. So then we've created a big problem. We've created a situation where we've get into the weeds here, but in a galvanized steel surface, there's a process called passivation, which creates a protective layer. Basically, in the beginning of its life, we keep the pH extremely neutral for a period of time, and that allows a protective layer to form on that galvanized surface. I think it's zinc carbonate?
Something like that.
I think it's zinc carbonate layer. And so that creates a surface that protects the zinc, which protects the steel. Well, as soon as we start hitting those surfaces with acid, we lose that zinc carbonate layer, and then the actual zinc becomes a sacrificial.
Not good.
Not good. And then you have to replace the coils. And replacing the coils on a fluid cooler, we love those calls because they're very expensive. No, actually, we don't like the calls because it means that, a customer of ours is dealing with a really difficult situation. So long story short, galvanized coils, cheap, decent heat transfer, but very subject to miscalculations on weather chemistry, and they have a limited life expectancy, and they're very expensive to replace.
Especially if you're draining the coil in the wintertime, which some people will do.
Yes. Is there any type of aftermarket coating?
Well, the inside of the coil's not zinc coated.
Sure.
So it's just carbon steel. So when we drain it, like you referenced there, Spencer, sorry to interrupt you, we've now dried it out. So now we had wet, and now we're adding oxygen.
Not good.
Which is a recipe for rust.
Yep.
So big problem.
So you either need to add glycol to your coil loop, or you need to get a different coil.
If I had a galvanized steel fluid cooler, I would do everything I could to make sure that it has galvanized, or that it's using glycol in there for freeze protection and for corrosion resistance, which is more expensive. Go ahead, Brian. You had a question.
Has there ever been a product solution for an aftermarket coating once the zinc is worn off, or
not really? No, you're going to spend more money pulling that coil section out, having it mechanically clean, and then recoated with zinc. You're just going to replace the coil.
Not very feasible.
No.
So all those things lead you to there's stainless steel coils. We'll skip that for time.
Do you want to hit stainless real quick?
You hit it, and then we'll talk copper.
Stainless steel coils are available in the fluid cooler market. We offer them. Marley offers them. I think the other competitors do too.
Yeah, superior corrosion resistance.
Obviously, superior corrosion resistance. You cannot. I mean, it's impervious to most chemical treatment mistakes. It doesn't have as good of a heat transfer as the galvanized steel. And it's nowhere close to the heat transfer of copper, which you already alluded to before, is your hands down favorite pick. Stainless steel is also the most expensive.
Yeah, boo.
Yeah.
And it supports the Russians.
So if we want a corrosion resistant material, chemically resistant material, and the best heat transfer, and we don't want to spend as much on stainless, we choose
copper, ding, 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 ding.
Exactly.
And sometimes, Troy, the copper coil can be so much more thermal efficient, it'll put you into a smaller box size.
Yep. And sometimes lower pressure drop. And
yep. So sometimes the coil itself is more, but the overall price of the equipment is less.
Yeah. This kind of reminds me of when we did the Counterflow versus Crossflow competition. And we said, all right, hands down winner is the Crossflow cooling tower for all of these reasons. But there's a place for a Counterflow tower.
Sure.
Hands down winner for materials of construction in a fluid cooler, copper.
Yeah.
Copper. What's the only reason that we would not, this is maybe a trick question, that we would not supply or that we would not recommend a copper coil in a fluid cooler?
If the lead time, no.
All right. Okay. Two good reasons. Number one, if the lead time doesn't permit it. And number two is if Marley hasn't developed that product yet. Because I was going to say not every fluid cooler that they have is copper capable. Is that correct?
I think they're getting pretty close to having most of them. There is a non-hybrid fluid cooler that we have, a Counterflow standard, not a hybrid, the DT, which they don't have copper coil, I
Okay.
don't think. But they do have the elliptical finned coil, so you get more efficient with the fins.
But wait, Spencer,
But wait.
I can't specify a copper fluid cooler because not everybody else does it. It's not fair
Oh,
to everybody else. How do we deal with that?
life is not fair. No, actually, we had a project where this exact thing happened, and we're always honest with our engineers. We play the long game, right? So in that scenario, I just explained all the benefits of the copper, and I flat told them my competitor could not do this, but here's what you can allow for them. And I advise they allow stainless steel for the competitor.
Right.
That gives you the corrosion resistance.
Yep.
That is really, in that case, was the main reason we were doing it.
Yep.
So
And why are we fine recommending stainless as an option? Because it's more expensive. Well, I don't mean that. I don't mean that in a bad way.
Yeah.
I mean, I think we're maintaining integrity there.
we should
to
not
say,
be punished for having better products.
yeah, it's a better product and it's less expensive.
Correct.
So other people can bid on that, and if they can miraculously get that stainless steel,
Allow them to quote their more expensive option.
Right.
That's fair game.
Yep.
The client should not suffer because someone else is not up to our speed.
right, exactly.
For sure.
Any
Last thing on copper before we move on. If you do happen to not put glycol in the system and you burst your coil, you can recycle your copper and
So
reclaim
much
some of your
easier
investment.
to
Yeah.
repair a copper coil.
Yeah, I
than
didn't
it
even
is
think about
a
that.
steel coil as
Yeah.
well.
But if you wanted to replace it,
Yeah,
you can get some money back for that copper. I don't think you're going to get much, if anything, for your galvanized coil.
very true.
Yeah. So
Very
sorry,
true.
Brian.
How much time? How long are we?
That's a great question. I was going to say it's time for closing comments,
Oh.
and we promised in a championship rib recipe.
Shoot.
Uh-oh.
But I feel like we could talk so much longer about fluid coolers. We're such nerds.
Maybe we'll do a follow-up episode.
Okay.
All right. So,
All
closing
right.
comments on fluid coolers. We like them. We like them a lot.
I
we-
love fluid coolers.
There's going to be a display of I heart fluid coolers here. One thing that's great, a little commercial plug about Marley SPX, is they have literally patented. They have almost all the patents in the industry, and they have every type of fluid cooler available, both forced draft, induced draft, counterflow, crossflow, galvanized steel, copper coil, stainless coil. We love it because we don't have an axe to grind other than making sure that we're making the right recommendation for the application.
It's super valuable for customers because they get an unbiased opinion.
Right.
We have it all, so really it's about your application. I'm not going to pigeonhole you or guide you down the wrong path because I only have a certain product. No,
Right.
You're open to everything. What do you actually need for your
But
project?
all of that being said, if we had our choice, we would probably specify a copper coil, induced draft, crossflow, hybrid fluid cooler.
Yes, for larger tonnages.
Right.
For probably 150, maybe 200 tons and under. I like the LW. It is counterflow. That's the only thing different between the MHF.
But it does have the ECM motors on it.
It's got the
when they're
ECM motors
available.
if you want them, but it's got the direct drive fans. It's plug and play controls. Installation is so much easier than a standard fluid cooler or standard cooling tower.
Right.
It's a great product.
Okay. So LW
Yep.
and
MHF element.
MHF element. Okay. That's it. Now,
Represent.
for what everybody has stuck around for is championship rib recipe. And this is a championship rib recipe because we had a smoke off in our St. Louis office, and I humiliated Jeff Henderson.
Wow, you just threw his name out.
Oh, yeah, I
To the
am.
entire
You should've
United
just-
States.
Jeff Henderson lost big time.
So there was 2 contestants.
Yeah, there were 2 contestants. You didn't have to call that part out. But here it is. And here's what I love about the recipe. It is super simple. It can be a last-minute recipe or a 24-hour recipe. So go wherever you like to get your ribs, Sam's, Costco, your butcher, baby backs. I like if I'm looking at 2 slabs of ribs, I want the meatier ones than the smaller ones.
Yeah.
Makes a difference. And then if you're at your butcher shop, they'll almost always have peel the membrane off. Super important to
Gotta
peel
take
the
that
back silver membrane off. Sam's Club, Costco doesn't do it, but it's very easy. Just grab a paper towel and just tear it off as you go. Get your favorite rub. I have a favorite rub. Spencer, are you going to divulge your favorite rub? Mine is go to Cabela's, and it's their sweet rib rub. And this is a crowd pleaser. What's your favorite rub?
I am hooked on Cimarron Docks.
Which I've never tried. We're going to pick some up on the way out of
Yeah.
here today. Cimarron Docks or Cabela's sweet rib rub. And just load up both sides of your ribs. Put them in the fridge overnight. Get your smoker. We all use pellet smokers. I think within our company we have about 30 of them. We're very competitive grillers in this company. But get your smoker to high heat or high smoke, which is typically 210 degrees.
Yeah.
And just put those babies on the smoker. I'm not doing 3, 2, 1. I'm not wrapping them. I'm not putting mustard on them. I'm not doing any of
Don't mess
that.
with it.
Straight on the smoker. No mop. No nothing. Sometimes I'll touch it up with a little bit more rub. You don't want to put too much on there because you can over sweeten or over salty it. And you just let those ribs go for about 4.5 hours. You'll know they're done when the meat pulls away about a 1/4 inch from the end of the bone.
Yep.
4.5 hours, lop off, and then rib. Test it to see if it's what you want. You don't want to pick up a slab of ribs in the middle and it fall apart. You want it to be springy and bouncy right before it falls apart. Just before it falls apart. And no sauce. Serve it as is. If you have a bunch of communists that you're serving for that demand sauce, put the sauce on the side. And if they're very powerful communists, like maybe a wife or something, very lightly baste them in the last 15 minutes.
If you do have to use a sauce, get more of a marmalade so it glazes nicely instead of a runny sauce and sticks on it.
This recipe beat all the 3, 2, 1 rib recipes, and it's the easiest recipe I've ever done. That's it. Give us feedback if you try it. Let us know if you're a hero at your next barbecue.
Sweet.
Thank you, Troy and Spencer, for being on Engineering Tomorrow. Again, the best compliment you can give us is a follow on YouTube, as well as a follow on iTunes or Spotify, SoundCloud.
No, the best compliment is give us a call on your next cooling tower, pump boiler,
There we go.
fluid cooler,
water
any of your
source,
HVAC or cooling or heating needs. Give us a call. That's the best compliment we can get.
Yeah.
And what's the best way to reach Midwest Machinery for that?
Just our website, midwestmachinery.net. We've got links to different locations so that you can find Spencer or a team in Oklahoma or a team in St. Louis or a team even in Denver.
All right. Until next time, thank you all again, and keep engineering for tomorrow today.
Thank you.
Thanks for joining us on Engineering Tomorrow. If you liked the show, please take a moment to subscribe on iTunes or Spotify. For even more great engineering or construction knowledge, visit engineeringtomorrow.blog.